So it indicates if a substance is present. So that's what this chemical dimethylglyoxine does. If it turns pink, there's nickel there. There's different ways to test, and I've listed some down below. There's gas tests. Remember, if it pops, it's hydrogen. There's pH paper, conductivity, flame tests, the color of a flame, the color of solutions. So that only tells you whether a substance is present. It doesn't tell you how much of a substance is present. Quantitative analysis is used to determine how much. And this is a really a key process in forensic analysis or water quality analysis. You need to be able to test how much of a substance is actually present. They use this in urine analysis, blood analysis, water analysis, food and beverage analysis. You probably don't remember. There was a number of years ago when baby formula coming from another country had a high content of plastic in it.
That's totally something you should feed a child.
Yeah. They used it as filler. And then have you heard, what's it called? There's a term, I can't remember, maybe you young minds can remember this stuff better. Black Earth. There's a term for manure. I think it's called black earth or night soil, maybe?
Sure.
I think it's night soil. That's basically human waste is used as fertilizer, which is not good, unless, of course, you're on Mars. If you've seen that movie, The Martian.
We watched it in Green Industries.
It's not good because if it's not treated it's a great fertilizer if it's treated properly, but if it's not treated properly, you've got an opportunity for poison to happen. That's happening in North Korea. Are you aware of recently there was a North Korean soldier that made it across the DMZ? And he was shot, so they had to deal with that, but they also had to deal with all of the parasites in his body. Full of parasites. And that's because they use this night soil, which is not treated. So it just gets passed through the food chain, spread on the fields, and then it gets back into people. So people are starving because these parasites are eating them from the inside. Oh, nobody just had breakfast. Okay. So we are going to skip to the next page. Partway down where it says quantitative analysis. Just, public service. Okay, quantitative analysis. You ready? Right there. Stoichiometry will allow us to determine yields and limiting reagents just like we did before. The only difference will be that we start with concentration and volume rather than mass and molar mass. Hold on. What do you need? Gotcha. So we're going to start with example number 1. It says determine the minimum volume of a sodium sulfate solution that is required to react completely with all the barium ions in a 500 mils of 0.1 molar barium chloride solution. It's a lot of stuff. So what I want you to do right now is underneath that balanced chemical equation, I want you to list the information that we know about each substance. Okay. I've already changed my volume into liters because we have to use liters when we do our math. So when I write down my volumes, I always divide the milliliters by 1,000. To get my volume. So the question wants to know the volume of sodium sulfate that we need. So we're looking for this volume. What do you think we're going to have to use that we haven't written down? It's on the page, but we haven't written it down separately. It's 2 words. One starts with M. No, but you're close. One word starts with M, the other starts with an R. That's LR. M. Mole ratio. We're going to have to use mole ratios. This is a stoichiometry question, so you're going to have to use mole ratios. We've got information about barium chloride, so we can find moles. We need to find liters of this, so we need to know moles of this. And the reason we're talking about moles and volume is because C is moles per liter, N over V. It's a 1-to-1 ratio. So you can either write a statement, because it's a 1-to-1 ratio, there's 0.05 moles of sodium sulfate, or actually show it. In university, you're not going to get away with sticking that value in the next step if you don't convert it. You have to either have a statement showing conversion or actually work it out. So moles of sodium sulfate is equal to 0.05000 moles barium chloride times 1 sodium sulfate for every 1 barium chloride. The best solutions are the complete solutions. So we have 0.05 moles of sodium sulfate. You with me? Okay. rearrange that formula so we can solve for our unknown, which is volume. So 0.05 divided by 0.42 moles per liter. And our answer is Billy? 0.119 liters.
Oh, yeah, liters, sorry.
Okay.
I got the same thing doing C1, V1 equals C2, V2.
Okay, so what you have, it works because it's a 1-to-1 ratio.
Yeah,
If it's a 1-to-2 ratio, one of them is going to be a half.
okay.
Okay, so you can do that if you follow that. Make sure that you know which side the half goes on. Okay, so 119 milliliters. Right? Okay. Yeah, we want liters of sodium sulfate. What quantity that we have out of those four has liters with sodium sulfate in it? Leah? Yes. So we want liters in our final answer, so you have to invert that. Because liters is on the bottom. So 1 liter of sodium sulfate, because it's per liter, contains 0.42 moles. You okay with that? It's per liter or per 1 liter. So 1 liter of sodium sulfate over 0.42 moles. So we want to get rid of moles of sodium sulfate. So that will be our mole ratio. So now we've got moles of barium chloride. So we have to use our concentration because that has moles in it. We get rid of moles of barium chloride. But we've got liters of barium chloride. So if we multiply that by 0.5 liters, now that unit is gone too. So you would take 1 times 0.1 times 0.5. And you would divide it by 0.42. And you should end up with the same value of 119 milliliters, or 0.119. All right? You guys okay with that? you guys have it balanced yet? Matthew does. Janae, do you? Trying?
I was actually.
Okay. You think? Okay.
So I have 3, 2, 4.
Okay, 3, 2, 6, and then nothing. 6 nitrates, 6 nitrates, 6 sodiums, 3 carbonates. Looks good. All right, so formulas, then dimensional analysis. Okay, so formula people. You've got to figure out the moles of each reagent and then convert them to moles of product and then grams of product so that you can see which one gives you the smallest mass. It is a lot of work.
Yeah.
Dimensional analysis, we're going to set it up exactly the same way that we did before, with the molar mass of our product first, but the last part in will be our concentration and our volume. So, this is 1.5 liters and 0.8, oops, mole per liter. This is 0.85 liters, 1 mole per liter. Bless you. Okay. So you've got V, you've got C, you need to figure out moles. So you multiply those numbers. 1.5 liters times 0.8 mole per liter, and 0.85 liters times 1. What do you get when you multiply 1.5 times 0.8? Is it 0.12? 1.5 times 0.8. Oh, 1.2. 1.2. Thank you. So now we've got moles of our starting reagents. You have to figure out which one is limiting. So which one produces the least amount of moles of your product? So you have to convert both of those moles to moles of aluminum carbonate, your solid product. So you're going to multiply the first one, 1 aluminum carbonate, for every 3 sodium carbonates. And you're going to multiply the second one by 1 aluminum carbonate for every 2 aluminum nitrates. Which one of these numbers is smaller? Ben?
0.3.
The 0.3. So that is the most amount of product we can make. It's not the final answer because it's not mass, but that means that sodium carbonate is the limiting reagent because it limits how much product you can make. So, yep,
Isn't that 0.4? No, it's 0.3.
yes, sorry. 0.4, thank you. No, that's not, that's right, that's wrong. Yep, 12 divided by 3 is 4. Still. Thanks, Kai. Okay, so we've limited how much product we can make. This is the smallest amount. So what you need to do now, to finish this question, find the molar mass of aluminum carbonate, multiply that by the number of moles to figure out the maximum mass of precipitate. So, you guys are going to work on that. Dimensional analysis. This question is missing one piece of key information that we need, and that's the molar mass of aluminum carbonate. Did you figure it out already?
Yeah. So molar mass is 195.00.
Dimensional analysis, we are looking for grams of aluminum carbonate. So we have to start with the molar mass of aluminum carbonate because it has grams in it. Okay, so we're going to start with the molar mass of aluminum carbonate. I should have picked something without polyatomic ions. Okay, so I have to get rid of moles of aluminum carbonate. To do that, I need the mole ratio. There's 1 mole of aluminum carbonate for every 2 moles of aluminum nitrate. So the next step has to have moles of aluminum nitrate in, so you have to use your concentration. So that gets rid of moles, and then you have to multiply it by the volume to get rid of the liters. Now you're going to repeat that with sodium carbonate. So you start with the molar mass again. So once you've got that, you need your mole ratio of your product to your reactant. That gets rid of those moles. Now multiply it by the concentration. That gets rid of the moles of sodium carbonate. And then you multiply it by the last thing is the volume. Do those calculations. The smallest mass is your theoretical mass, your theoretical yield.